Next is about Gibbs energy, chemical potential, chemical kinetics. So Gibbs energy, often denoted as G, is a fundamental thermodynamic concept that plays a crucial role in understanding chemical processes, phase transitions, and spontaneity of reactions. It is named after the American scientist J. Willard Gibbs and is also referred to as Gibbs free energy or Gibbs function. Understanding Gibbs energy is essential for students, educators, and professionals in the field of chemistry and thermodynamics. Definition of Gibbs energy. Gibbs energy is defined as the maximum reversible work that can be performed by a system at constant temperature and pressure when it undergoes a spontaneous process. So, spontaneity of reactions. Gibbs energy is used to determine whether a chemical reaction is spontaneous or non-spontaneous. If delta G is negative, the reaction is spontaneous or exergonic. If delta G is positive, the reaction is non-spontaneous or endergonic. And if delta G is 0, the system is at equilibrium. So if delta G is positive, the reaction is non-spontaneous, endergonic. Okay, don't forget that. Delta G positive, reaction is non-spontaneous, endergonic. Phase transitions. Delta G also helps predict phase transitions such as the conversion of a substance from solid to liquid or liquid to gas. For a phase transition, delta G equals 0 at equilibrium. Then chemical equilibrium. In a chemical reaction at equilibrium, delta G equals 0, indicating that the rates of the forward and reverse reactions are equal. Then chemical potential. Gibbs energy is related to the chemical potential of a substance, which represents the tendency of a substance to move or react. Chemical potential is often expressed as delta G by delta N, where delta N is the change in the number of moles of the substance. Then chemical potential mu. The chemical potential denoted as mu is a fundamental concept in thermodynamics and mechanics. Statistical mechanics. It represents the potential energy of a substance per unit quantity and provides insights into phase equilibria, chemical reactions, and the basis of behavior of particles in a system. Phase equilibria. Chemical potential is crucial in understanding phase equilibria such as vapor-liquid equilibrium. In a two-phase system, the chemical potential of a substance is the same in both phases at equilibrium. Then chemical reactions. Chemical potential helps predict and understand the direction of chemical reactions. In a closed system, a spontaneous reaction occurs when the chemical potential of the reactants is greater than that of the products. Then fugacity. Fugacity is a related concept used in non-ideal systems to describe the deviation from ideal behavior. It accounts for deviations from ideal gas behavior and is related to chemical potential. Then chemical kinetics. Chemical kinetics is a study of the rates of chemical reactions and the factors that influence reaction rates. It provides insights into reaction mechanisms, reaction orders, and reaction rate equations, helping us understand how quickly reactants are transformed into products. Then key concepts and significance. Rate of reaction. Chemical kinetics quantifies the rate of reaction, which is expressed as the change in concentration of reactants or products per unit time. Then chemical kinetics. Chemical kinetics is the study of the rates of chemical reactions and the factors that influence reaction rates. It provides insight into reaction mechanisms, reaction orders, and reaction rate equations, helping us understand how quickly reactions are transformed into products. Reactants are transformed into products. Then key concepts and significance. Rate of reaction. Chemical kinetic quantifies the rate of reaction when is expressed as the change in concentration of reactants or products per unit time. Then rate law. The rate law of a reaction relates the rate of reaction to the concentrations of reactants. It is determined experimentally and provides information about the reaction's order and rate constant. Then reaction mechanisms. Chemical kinetics helps elucidate reaction mechanisms by which reactants are transferred into products. It involves identifying intermediate species and sequence of elementary reactions. Then reaction rate factors. Factors affecting reaction rates include temperature, concentration, catalysts, and surface area. Arrhenius equation relates temperature and rate constants. Then reaction order. Reaction order describes how the concentration of reactant affects the reaction rate. It can be zero order, first order, or second order. Then chemical equilibria, solubility of gases in water in detail. Chemical equilibria. Chemical equilibria are a fundamental concept in chemistry that describes the balance between forward and reverse reactions in a chemical system. Equilibrium is a dynamic state where the rates of forward and reverse reactions are equal and concentrations of reactants and products remain constant over time. So, understanding chemical equilibria is crucial for students, educators, and professionals in the field of chemistry and thermodynamics. So, key concepts in chemical equilibria. Equilibrium constant K. The equilibrium constant K is a mathematical expression representing the ratio of product concentrations to reactant concentrations at equilibrium. It varies with temperature and provides information about the extent of a reaction at equilibrium. So, reaction quotient Q. Reaction quotient Q is similar to the equilibrium constant but can be calculated at any point during a reaction, not just at equilibrium. It helps predict the direction in which a reaction will proceed. Le Chatelier principle. Le Chatelier principle states that if an external change is imposed on a system at equilibrium, the system will adjust itself to counteract the change. This principle is applied to predict how changes in concentration, pressure, temperature, and volume affect equilibrium positions. Then heterogeneous equilibrium. These involve reactions in which reactants and products are in different physical states, solid, liquid, and gas. The concentrations of solid and pure liquids is typically treated as a constant in equilibrium expressions. Then application of chemical equilibria, industrial processes. Chemical equilibria are essential in the design and optimization of industrial processes such as ammonia synthesis, Haber-Bosch process for fertilizer production, and petroleum refining. Then environmental chemistry. Understanding equilibrium reactions is crucial in environmental chemistry, especially in the study of acid-base equilibria, dissolution of minerals, and pollutant reactions. Then chemical analysis. Equilibrium reactions are used in analytical chemistry for quantitative analysis, just determining concentrations through titration methods. And solubility of gases in water. The solubility of gases in water is a vital aspect of physical chemistry, describing the ability of gases to dissolve in aqueous solution. It plays a significant role in environmental science, biology, and industrial process. Understanding gas solubility in water is essential for students, educators, and professionals in chemistry and related fields. Key concepts in gas solubility. Henry's law. Henry's law describes the relationship between the partial pressure of a gas and its concentration in a liquid at a constant temperature. It is expressed as H is Henry's constant. C is the concentration of gas in the liquid. So, gas exchange in nature. The solubility of gases like oxygen and carbon dioxide in water is critical for aquatic life. Fish and other aquatic organisms depend on dissolved oxygen for respiration, while CO2 dissolution influences ocean acidification. Then industrial applications are also there. Gas solubility in water is important in various industrial processes, including water treatment, carbonation of beverages, and extraction process. And Henry's law constants are specific for each gas solvent pair at a given temperature. They can be determined experimentally and are often tabulated for common gases. These constants are temperature dependent, meaning they change with temperature variations. Henry's law constants are specific for each gas solvent pair at a given temperature. They can be determined experimentally and are often tabulated for common gases. These constants are temperature dependent, meaning they change with temperature variations. And applications of gas solubility in water. Aquatic sciences. Understanding gas solubility is crucial for studying aquatic ecosystems, including the oxygen levels required to support aquatic life and the effects of temperature changes on dissolved gas concentrations. Then water treatment. Gas solubility plays a role in water treatment processes such as aeration to remove volatile organic compounds and the addition of chlorine for disinfection. Then carbonation. In the beverage industry, carbonates rely on controlling the solubility of carbon dioxide in water to create effervescent drinks. Then chemical engineering. Gas solubility is important in chemical engineering process such as the extraction of volatile compounds from liquids and the design of gas liquid contracts in reactors. So in conclusion, the understanding of chemical equilibrium and the solubility of gases in water are foundational concepts in chemistry and related fields. These concepts have broad applications in various scientific disciplines. Then unsaturated and saturated hydrocarbons, radioisotopes. The carbonate system. The carbonate system is a fundamental concept in chemistry and oceanography that describes the equilibrium between dissolved inorganic carbon species in water, including carbon dioxide, bicarbonate ions, and bicarbonate along with carbonate ions. The system has important implications for ocean chemistry, climate, and global carbon cycle. Key concepts in carbonate system. Carbon dioxide, atmospheric CO2 dissolves in water, leading to the formation of carbonic acid, which dissociates into bicarbonate ions and hydrogen ions. When bicarbonate ions, these ions are formed when carbonic acid dissociates further. They are dominant species in most natural waters. So carbonate ions, when bicarbonate ions further lose a hydrogen atom, they form bicarbonate ions, which are less abundant in neutral water but still significant. Equilibrium constants in the carbonate system. The carbonate system can be described by equilibrium constants, K value, that relate to the concentrations of the various species. Then equilibrium constant for carbon dioxide in a solution. Significance and applications of carbonate system. Ocean acidification. Understanding the carbonate system is critical for studying ocean acidification, a consequence of increased atmospheric CO2 levels. As CO2 dissolves in seawater, it reduces carbonate ion concentrations, making it more challenging for marine organisms with calcium carbonate shells and skeletons. Then climate regulation. The carbonate system plays a crucial role in regulating atmospheric CO2 levels as the ocean acts as a carbon sink. So changes in the carbonate system can impact the global carbon cycle and climate. And chemical oceanography. It provides insights into the chemical composition of seawater, including its alkalinity and buffering capacity. Then unsaturated and saturated hydrocarbons. Unsaturated and saturated hydrocarbons are two distinct classes of organic compounds composed solely of carbon and hydrogen atoms. They differ in the type of carbon-carbon bonds present in their structure. Then saturated hydrocarbons. Saturated hydrocarbons, also known as alkanes, are organic compounds in which all carbon-carbon bonds are single bonds, sigma bonds. They are called saturated because each carbon atom is bounded to the maximum number of hydrogen atoms possible. The general formula for saturated hydrocarbons is CnH2n plus 2, where n is the number of carbon atoms. Key characteristics of saturated hydrocarbons. All carbon-carbon bonds are single bonds, sigma bonds. They are relatively unreactive compared to unsaturated hydrocarbons. Examples include methane, ethane, and propane. Unsaturated hydrocarbons. Unsaturated hydrocarbons are organic compounds that contain one or more carbon-carbon double bonds, pi bonds actually, or triple bonds. There are two main classes of unsaturated hydrocarbons, alkenes and alkynes. Then alkenes have one or more carbon-carbon double bonds. The general formula for alkenes is CnH2n. Example, ethene. Alkynes contain one or more carbon-carbon triple bonds. Example, ethyne, acetylene. Key characteristics of unsaturated hydrocarbons. They contain one or more carbon-carbon double or triple bonds, pi bonds actually. So unsaturated hydrocarbons are more reactive than saturated hydrocarbons due to the presence of multiple bonds. They can undergo addition reactions, whereas atoms or groups are added to the double or triple bonds. Significance and applications. Fuel sources. Saturated hydrocarbons such as alkenes are commonly found in fossil fuels like gasoline, diesel, and natural gas. Unsaturated hydrocarbons are less common as fuels but are used in some industrial processes. In chemical synthesis, Unsaturated hydrocarbons serve as important starting materials in the chemical industry for the synthesis of various organic compounds. Then polymer production. Alkenes are essential in equilibrium in production of polymers like polyethylene, polypropylene and polyvinyl chloride. Next is about radioisotopes, which we will be learning with the help of next video. Thank you.